Hello and welcome to lecture number 9. Starting this lecture, we will see all the concurrent assertion operators. These are the operators that pretty much make up the bulk of the language, and there are quite a few of those. We will look at those mostly in single lectures, or maybe a few of them combined in a single lecture. So let's start with the clock delay operator that we have actually seen a few times. But for the sake of completeness, here's the pound M delay operator. M can be 0 here, that means there is no delay, or M can be a positive integer. Obviously, time cannot advance backwards, so it cannot be negative integer. And as I've said before in previous lectures, do not confuse this with the Verilog pound delay. Luckily, the syntax is that there are 2 pound signs here, so the chances of a mistake are very less. So in this property, we have seen this property many times before. Here's a property at pause edge of clock. Z implies, if Z is true, implies starting the same clock, this sequence should hold. And that sequence basically say A must be followed by B 2 clocks later. We assert the property and then we cover the property. And if during assertion, if it fails, we call this task. And during cover, if it is covered, meaning if it passes, then we call this task. So here's a very simple log of this property that I've simulated. And as you can see, at pause edge of clock, if Z is 1, then A must be 1 at the same clock and B should be 1 2 clocks later. That indeed happens here, and the property passes. Here, clock is 1 at pause edge of clock, Z is 1, and A is also 1 exactly as required, but B is not 1 2 clocks later, and the property fails. For the rest of the lectures in this course, I will not be showing this particular code because I'm going to use this code pretty much everywhere. In short, I will only show the sequence and property, and then I will show you a log with pass and fail. Where does this pass and fail come from? It comes from this code. So assume that this code exists during the rest of the lecture. Okay, now let's look at the clock delay range operator. So here we are saying that in this sequence, B must follow A within 1 to 3 clocks. It can follow A 1 clock later or 2 clocks later, 1 clock later or 2 clocks later or 3 clocks later. That's why it's called a range delay operator. M can be 0, N can be 0 or infinite. And I will show you an example on how infinite actually works. And obviously, if it is 0, 0 colon 0 is the same as 0, what that means is both A and B should occur at the same time, which is no delay, 0 delay. And obviously, again, M and N must be greater than 0. The thing to notice in all the operators is when does the property pass, or when does the property become true, so to say. Now in this example, we are saying that property AB at pause edge of clock, Z being true, implies starting the same clock, SAB should hold. Now SAB, so here's your Z, and A comes at the same time, which is correct. Now B can come either 1 clock later, 2 clocks later, or 3 clocks later, as I just described. That means if B comes 1 clock later, then the property passes and completes. It does not then look for B on the 2nd or the 3rd clock. If the B comes on the 2nd clock, not the 1st clock, then the property will pass on the 2nd clock. And same for the 3rd clock. So the property will match the very first time B is true. It does not keep looking for further Bs, which is something important to understand, because in other operators, the property will match at the last of the occurrence of a given signal. Here is the first occurrence of the signal. And here's a very simple application which you can apply. This one says that at passage of clock, if read request is asserted is high, is not edge sensitive, is level sensitive, they're starting the same clock. Within 1 to 5 clocks, either data ready should be asserted, should be high, or data abort should be high, which makes sense. After read request, either you are going to read or you're going to abort. And so, as you can see, range operator is very, very desirable, because in hardware, more than often you don't know exactly when the next event is going to occur. Now, this slide is probably one of the most important slides in this course. We saw multi-threaded with single delay earlier in one of the previous lectures. Now let's look at what happens. How does the multiple threads work with a range delay operator? So let's look at this example. At passage of clock, if ready is high, it implies starting same clock within 1 to 5 clocks, ready X should arrive. Okay. Here's your timing diagram. You have clock, ready, and ready X. Now let's say that on this passage of clock, S1 is the name of the thread, for example. At this passage of clock, ready is high, as required here. Ready is high. Then 1, 2, 3, and 4 clocks later, ready X arrives. And you will see the reason why I call it S1-2 in just a second. But 4 clocks later, ready X arrives, as you can see here. And since it was supposed to arrive within 1 to 5 clocks, the requirement is met and the property passes. Now let's say that ready comes again, the very next clock. What's going to happen? This ready is also going to wait from within 1 to 5 clocks to see if ready X arrives. Well, guess what? After this ready arrives, you have 1, 2, and 3 clocks, and 3 clocks later, it detects that ready X has arrived. So it's going to say, hey, my requirement is met as well, and it's also going to pass. Now see what has happened here. 2 readies came, but the simulation will show you that they both pass at this particular edge. How do you know if the ready X for S2 arrived or the ready X for the S1 arrived? You don't know that. Both of these are going to pass at the same time, and you don't know. What if the ready X for S2 did not arrive, but it sees the ready X that arrived for S1 and assumes that that is my ready X and passes? This is multi-threading, and this is very important to understand, because what you are getting here could be, not necessarily, but could be a false positive. Evaluation of both threads will end at the same time, because both were expecting ready X to occur in a range of delays. Ready X occurred within that range for both threads. Pay very close attention to it. So, first question is, this is dangerous. How can I be sure that the ready X for S2 also arrived? There is a solution for it, and that solution requires the use of something called local variables. And I have not covered local variables until now, so I will refrain from showing the solution to this problem until we go to local variables, where I'll repeat this example and show you how this can be solved, because this must be solved. Otherwise, you may get false positives. So here's an application of range delay operator. And again, as I said, dollar meaning infinite can be very useful, because most of the time in complex sequences, we will not, or you will not know really when a certain signal or sequence will follow another signal, another sequence. But you do need to make sure that it does occur. So let's take an example. If tag error is detected, but the pipeline latencies are such that you don't really know exactly when tag error bit will be asserted. But whenever it is asserted, we don't know when, that the machine check is asserted the same clock. This is the spec that you will normally see in your microarchitecture hardware design specs, and you need to write an assertion for it. So here's your tag error. Here, okay, let me go. So here's the assertion. What we are saying is, if tag error is detected, always when you want to write an assertion, think of what your antecedent is and carefully design the antecedent. Without a carefully designed antecedent, the rest of the design of the assertion may be very cumbersome or difficult or even impossible. So when I read this spec, I'm saying that everything starts when tag error is detected. So I say $rows tag error. I wanted an edge sensitive because I only want to detect one tag error only when it occurs. Now I'm saying that I do not know when T error bit will be asserted, but it needs to be asserted. So what I'm going to do is pound 1 to infinity. I do not know when. But during starting the next clock up to whenever, this T error bit must go high. And whenever it goes high, M check is asserted the same clock. That's why I have pound 0. So this and this can occur at the same time. Now, you can also use and Boolean here, which will work the same way. I prefer pound 0 because what I like to see a continuum, a continuous temporal domain associativity to see how the temporal domain is moving forward. I personally don't like to mix Boolean with temporal domain, combinatorial with temporal domain. That's just my preference. It's up to you how you want to design it. There is no difference. There's nothing wrong either way. So here's the $rows tag error. And note that my arrow stops at the clock edge because it's at the pause edge of clock edge that we are going to sample in the pre-pond region if tag error is 1. And in the previous clock, in the pre-pond region, tag error was 0. And hence we detect $rows tag error. Then after that, 1 clock later, which is what this pound 1 means. So after this, for 1 clock, after 1 clock, we wait forever till T error bit goes high. It's an edge sensitive. And whenever it goes high, we make sure that M check also goes high. And if this relationship is met, then we'll say that the property passes. If not, then the property will fail, if any of this thing fails. Now, just for the sake of completeness, what happens, for example, if T error bit never arrives? We are waiting forever. Simulation ends, T error bit never arrived, and if the T error bit never arrives, we don't check for the M check. Some simulators will give an incomplete assertion. Some simulators may give a failure. And in the 2009 and 2012 LRM, there is a concept of strong and weak properties, which I will cover later. Depending on how you have defined an assertion, strong or weak, you will either get a failure at the end of the simulation if T error bit never arrives, or you will get an incomplete indication, which is dependent on the simulator. But we'll keep that aside. But I just want you to make a note of it, that there's a good chance T error bit never arrives. and what is it that your simulator is going to do. And that also depends on whether the property is strong or weak. So that's pretty much it for this particular lecture. Very simple clock delay operator we have discussed and you have seen in previous lectures, and also the range clock delay operator. Thank you for attending the lecture, and I'll see you soon in the next lecture.